Hello and welcome back. When we talked about relational databases before, we introduced the concept of a database schema. Now we want to take a much closer look. So what is the database schema? Let's take this quote which summarizes it quite well. A database schema specifies, on the basis of the database administrator's knowledge of possible applications, those facts which can enter the database or those of interest to possible users. So what is it again? Let's take the plain English version. So when we talk about relational database in particular, the schema describes how the database is constructed. In particular, it contains details about which tables we have in the database, which columns we have in those tables, and these columns correspond to the variables. And we also define which data type per column or per variable we have, for example, integer, floats, strings, datetime, and so on. The schema also specifies how these tables are related to each other, so that it stores the details about the relations. Let's take a simple example. We focus on experimental samples and storages, where we store those samples. So one option would be to have one big table where we have a sample name and a sample composition and the storage location and so on. That would work, but everything is centered now around the samples. That may not fit our use case later, and we may not be flexible enough to, for example, query what experiments that we use on these samples efficiently. Also, we need to store a lot of redundant information, especially if we have lots of more details about the experiments or the instruments and so on. Instead, we take the different route and we have many specialized tables, one per entity. In our minimal example here, we would have one table describing all the storage locations, so for example, a vacuum chamber or a cupboard or something like this. And we have one table that specifies all the details about the samples, but nothing else. And now we need to link those, and you can see here we have storage ID twice, once in the table for the samples and once in the table for the storages. So this is what's called the primary key. This is the ID of the table. We have the storage ID and the sample ID. So within those tables, samples and storages, the primary key identifies which element we have. For example, the row number could be a primary key. And then we have the data types, like for example the ID could be just an integer, but typically inside the database it's handled as an index data type. Our name is a string, and the last update we can also add to just reflect when any changes were made. But as we've alluded to before, the storage ID now appears twice, and this is where we have the foreign key concept. So the primary key in the storage table identifies the storage location inside the storage table. And now we want to link the sample with the storage. So which sample is in which storage location. And instead of writing, for example, in a string cupboard, we use the storage ID. And this is called the foreign key in the table of sample ID. Now the database now knows that we have this relationship because we have the primary key in the storage location table and the foreign key in the sample table. And we tell the database, here is a relation, and we do this via the primary foreign key. Now that the database knows about it, it can enforce it and can say whenever we want to, for example, enter a new storage location that is not yet known, it needs to be updated first in the location table. And then we do the same thing for many tables. The key concept is that we have one table per entity. We had now the sample and the location, but we will also have tables describing our scientific instruments or the experiments and so on. Each of these tables has appropriate data types for each column. So for example, our instruments will be described by a number of settings, and the software version, the make and the model and so on, and we specify fixed data types for each of them. Each table has its own primary key, and this is also to ensure that each row entry is unique, that we can't, for example, enter the same instrument twice. And then we use those primary keys as foreign keys in other tables to establish relationships. When we store data in a database, we need to organize it in tables. But what do we mean by that? And that's called normalization. Normalization means we group together what belongs together and how do we split tables to avoid redundant information. There are a number of ways to organize this. The simplest one is the first normal form, or 1NF. That means that we have single atomic columns or variables. So we don't use strings to store a bunch of details, but we have separate variables for each description we want to make. We have unique rows, so no duplicates, and we have unique columns, so that no variable appears twice. And we have no repeating groups, so that no variables or columns are very similar to each other. And the primary key is to identify each entry. So that's like the minimum set of requirements on a table. The next one adds that we have separate tables for information that is used in multiple records. We have already used that in our previous example, for example, the storage location. We could have integrated the storage location with the samples, but we use the storage location for different things maybe. Or, if you think ahead, we have scientific instruments. We have a number of samples that we use. And so we better put the instruments into the separate table as well. And then we can establish relationships via foreign keys. The third normal form adds as another requirement that we eliminate fields that do not depend on the key. So that there is no implicit or transitive dependency between variables and columns. It sounds a bit vague, but it's like, how do we organize the table and what kind of fields do we have? The key identifies what we have in the table, and if there is anything in that table that doesn't really describe the key, then we should not include it. So as a rule of thumb, make sure that each column or each variable appears only once. Each data field has only one entry, so there are no strings or ad hoc miscollection of properties or anything else I couldn't think of in variables. I'll just put in this very long string. If you have something, you maybe change your schema and amend it, but don't put a long string that groups everything together that you have forgotten in the first instance. Group things that belong together in their own table. If in doubt, make a new table rather than tack something on a table that you already have. It's better to do this cleanly rather than hack something together. Make sure that tables have a primary key and that each row in the table is unique, and then use the foreign keys to establish relationships. And then the database knows how to relate all those tables to each other. So what are the advantages of handling all of this? If we do this, we have a well-defined design of our data model. All the variables are defined and they have a fixed and definite data type. So that means we reduce the possibility of low data quality or errors entries. And we also have fixed and well-defined relations. Because lots of these details are fixed and predefined, the database engine can do many checks automatically. For example, the data format, the relations, uniqueness, and so on. And this is how you can enforce consistency throughout the database engine. Of course, it comes at a price. You can't have really ad hoc entries. If there's no appropriate table, or if there are no appropriate variables or columns in the table with the right type, you cannot enter such data. So you need to think about your data beforehand. Personally, I think this is a good thing. But if you really need that flexibility, then you need to go a different route. Also, it's not great if you need to store large data in a database. For example, if you really require that you store images and documents and files and so on in the data, within the database itself. This data model is only meant for essentially the metadata and not for petabytes of large data that needs to go in a separate storage system. So no ad hoc entries, right? If there's no table or column, you cannot enter such data, right? That's true, but you cannot enforce variable names and type, and this helps you to alleviate data equality issues afterwards. For example, misspellings or reuse of columns and so on. It's difficult to do queries if you don't know which variables are where and which spelling variants you have, or abbreviations, or what you look for. So ensuring that you have defined types and variables actually helps you take stock of the data later and organize it. You need to think about your data before, and I've just said it before as well, right? You need to do that anyway because you need to probably write your research data management plan, so you already have to think about which data you have and which data types you have and which variables and so on. As I said, it's not great if you need to store large data in a database, like lots of images, right? But really think if you really need to store them in this storage system. As we said in other videos, you will likely have a technology mix anyway, so you need to pick and choose which technology is best suited for which application. And then the general question is schema or no schema, right? So relational database relies on the schema, NoSQL database typically don't have a schema. What's right for you? As always, it depends. It depends on the use case or your application and your usage pattern. It also depends on how and who will interact with your system. Like, will you have a separate front-end system that interacts with the database, or will your users interact with the database more directly? The schema enforces consistent data and allows many checks, and this is a plus in many applications, but it also reduces flexibility. It helps with data quality because you can control more fine-grainedly how users can enter information, but that's less problematic if you capture most of the information automatically without much user interaction anyway. Remember that each new user brings a new set of things that you did not imagine a user could do with the system. So you really need to think about where do you require flexibility and where is it better to only limit the choice users can make. So schemata define a relational data models, including variables, data types and their relations, and you need to think about what kind of data you have when you want to establish a schema. It also enforces a consistent data treatment and makes many checks possible that leads to less data quality issues, allows complex queries and so on. Using normalization tells us how to organize data in tables and skis, but the schema is very rigid, and that may or may not be a good thing for the specific use case you have in mind.